All right. Today we're going to introduce some Excel examples for network design problems, continuing from the lecture that described how we would formulate these problems. But specifically, we're going to use Excel to do some of the network optimization modeling. Recall that there were multiple points where we can bring in modeling for demand allocation, for gravity methods for location problems, and then in more general sense, network optimization that can involve both location, production, distribution decisions for all those. So that's what we're going to talk about today. And what I want to do is give a little bit of background on how to use these models in Excel. So let me start with this presentation that will be available to all of you on the basics of installing Excel Solver, using Excel Solver, a comment about VBA, and then actually going through the examples. Now, I realize this should be a review, so we're not going to really talk about how to build a model from scratch using Solver. But the problems that I'm giving you as examples have a lot of the detail already in there, and they should be good starting points for building any model that we have as an exercise for the class. So we're going to look at how to access the Solver tool with Excel 2007 or 2010. Again, you can look at this, and hopefully all of you already have Solver on the current machine, but perhaps you've changed machines since the course you took where you had to use Excel Solver. So for completeness, we have these instructions here. For 2007, you'll want to go up to the Office button, click on Excel Options, and that will bring you to this next screen. And from here on the Excel Options, you want to select Add-ins for the Excel add-ins. Then on this drop-down button, make sure it says Excel add-ins down here, and then click Go. This will lead you to a subset of add-ins that deal with Solver, data analysis, items like this. So at a minimum, click on Solver add-in, but I use the analysis tool pack myself, so I would click on that too. That's up to you. Okay? And then when you come back to Excel, on the data ribbon over to the right, you'll be able to see the Solver is turned on. Okay. Now what I want to do is come over here and launch Microsoft Excel on this machine. And so under data, you can see that Solver's already been added in on this machine. So we'll come back to this in a few minutes. All right, if you're using Excel 2010, like me, actually on my desktop and laptop, I'm actually using Excel 2010. So we'll see if we have any issues between the two versions. We shouldn't. But they do have a different look and feel, especially on the Solver side, not really on how you add the Solver add-in. So again, so here when you open up Excel 2010, now you're going to go to File and then click on Options. Okay. So once you're at Options, now again you want to click on Add-ins and make sure Excel Add-ins is highlighted or is selected, and then hit Go. Okay, and again select Solver. Okay. So when we're actually developing a model in Excel Solver, This is where I'm assuming some prior knowledge, of course, on the use of the program, but all is not lost if it's been a while since you've used the tool. We will, of course, discuss it in our class, as well as the examples provide you some nice starting points. So if you're looking at this in Excel 2007, here's what it's going to look like. And let me get back there. Sorry about that. The changing cells is right here. That's really where the decisions are being made on what can we change in order to try to improve our result. So all the other cells in your spreadsheet are going to be fixed or dependent on what you put in, what you allow to be changed within this group of cells. The target cell is the particular cell that's representing our objective value, whether we're trying to minimize cost, maximize profit. And then we have the constraints down here for any restrictions on what we're allowed to change in the changing cells. Okay. In addition to that, we need to go over to options and indicate that we have either a linear model or non-negativity constraints to be assumed. Okay. So even though it says that the Solver 2007 options, they appear as options, but they're really not options. They're not optional in our case. So what we want to do is go into that, like I said, click on options, and you can click on assume linear model, assume non-negative, but we'll actually show that in our location allocation model in the chapter here we're discussing, we have binary decision variables on whether we open a plant or not, open a factory or not. So it's not strictly linear, and but we'll address that in how you deal with that answer. Okay. All right. If we're in 2010, this is the look and feel of the Solver parameter dialog box. So so we have set objective, which is the old target cell. And again, well, I didn't say this on the other one, but to make sure you show whether you're minimizing and maximizing and so on. Changing cells, constraints. Here, what they've done is move this to this front page so you don't have to select the solver in an options. And it seems to default to this the GRG nonlinear solver, and so typically you'll want to go in and switch that to LP simplex, even when we're solving an integer problem. Okay, so that's what this is showing. Okay, and then finally, solver combined with VBA. And what this allows is for somebody to have a front-end user interface on top of an Excel optimization model, where you can now provide different sets of input values that where you can actually run multiple optimization models and then compare and contrast the solutions that are coming out of each one. So this can be very important when you're actually trying to do some kind of an overall assessment of a production allocation scheme, where you're not necessarily confident that, yes, this is the precise amount of cost that will incur if we open up this facility, or these are the costs of per unit production and transportation. These different items may not be known with certainty, so you can kind of set some high and low cases for each of these, and then see if it leads to a different choice in how much you allocate to facilities and which facilities you open up. So the reason I bring it up, we're not going to build these VBA user interfaces on top of solver models, but the example problem network opt.xls has a command button on it that says solver, and we may encounter some issues when you try to open that up if the VBA code can't find solver. So we'll step through that, and I don't know if I'm going to even encounter that on this machine. I didn't want to pre-test it and then have it not appear when I actually show it to you. So VBA does need to find solver, and so the way that works is you need to go to Tools and References within the VBA code. And actually, I'll probably have to show you that too when we get to back into Excel. And once you look up references, you can find the one that says solver and then include it. Okay? All right. That's strange. I thought I had another slide at the end of this presentation, but it's a fairly simple slide that only said, let's begin looking at the examples. So let's just do that now. Okay. All right, so let's start with the first of these two. Let me go back to that page. And these are available, of course, with online for you. Figures 5.3 to 7 and network opt. So figures 5.3 to 7 is the first Excel file that I'm opening. And in your text chapter 5.pdf, I've got that open here. It's really starting, the discussion is in section 5.4, page 116 in the excerpt from the text. And we're looking at phase 2, network optimization models. So basically, we have a company that's Sunoil, manufacturer of petrochemical products, worldwide sales. And you have options to meet demand, several options. You can set up a facility in every region. And, of course, that'll lower transportation costs, but you also have the disadvantage of having to size facilities appropriate just for those local economies. It's not local demands, and it's not fully exploiting any economies of scale where we can group production together to meet a larger set of customers. So that consolidation trade-off. In the text, it's showing here some of the input values for the demand in each region, as well as all the production and transportation costs if you're to supply product from one particular region to another. We then have, over to the side, fixed costs for either low capacity or high capacity facilities that you can set up. Okay? Okay. What else do I want to kind of introduce you to here? Right, so here if you look at this part of the discussion, this is near the bottom of page 117. That Sunoil is considering two different plant sizes in each location, and low capacities are 10 million plants are 10 million units per year. High capacity plants are double that. Okay. All right. So let's come back in here to Excel, and let's look at how this is represented. So all this data is the same as what you just saw, and these are the input numbers that we're not changing. production and transportation costs per 1 million units to go from North America to North America, so local. If we're getting the supply from North America but sending it to South America, we have a cost of 92 to Europe, to Asia, to Africa. Okay? For South America, and again, you see the lowest cost in the local region, of course, and so that should be consistent for all of those, that they're lowest cost to supply in the local region and greater costs as you move further away. Okay? The demand in millions of units is located on this bottom column, or bottom row, sorry, for the 5 regions. Okay? Again, fixed costs, these are all inputs that do not change. Fixed costs for the low capacity, fixed costs for the high capacity. And notice that these are not doubled. In fact, they are all basically 50% increases in cost to get double the capacity. Okay? So we're going to move down to the decision variables. And these, again, there's no formulas behind any of these because they're all decision variables. These are the ones that will change as we select solve in Solver, and it will try to manipulate these values to arrive at the lowest cost and still meet all of our demands. And so what we're showing then here would be this whole set of decision variables are the demand allocation between demand and supply. Okay? And then here, plants. This indicates, since we have 2 columns, just like we had before for the 2 columns for low capacity and high capacity, although it's not shown here, this is whether we're going to open a low capacity plant or not, and this is when we're going to open a high capacity plant or not. Okay. So then we come down to the part where we actually have some formulas that will keep track of all this for us. What we need to do is ensure that we don't exceed capacity in any one of the regions and that we don't have unmet demand. Now there's different ways that you can set this up in Excel, and you may be comfortable with a certain way to combine cells, and this may not be your favorite way, but this is the way that we have in the sample model. So, for example, in North America, and if I double-click on this, we'll see what the relationships are. So what we're basically showing here is how much capacity we have, and then we subtract away the capacity used. And so what this says is G14 times H4, G14 times H4. So the total low capacity from North America plus H14 times G4 plus the total high capacity from North America. So that total amount is our total capacity, subtracting the demand that we use coming out of that region, or being supplied by that region. So we do that for each one of these. Let's look at one that actually has numbers in it, maybe. The Asia supply region. What it's showing here is that we open a high-capacity facility, giving us 20 million units, and then we use 4 million units to meet demand in Europe, and 16 million units of demand to meet, or supply to meet demand in Asia. So we have no leftover capacity, which is what the value shows. Okay, on the unmet demand side, now what we do is we take the total amount of demand minus where we've allocated it, and if that number is positive, we have leftover demand that we have not allocated or have met. So here we have 12 million units from North America being supplied by these 5 regions, and all of it is being supplied by South America. Okay, and then each one of these follows the same way. And then lastly, we have our objective function. So our objective function is going to minimize all costs. And if I look at this, I've got 3 components. The cost, I want to see if I can make sure I say this correctly, B14 to F14, of the demand allocation, B4. So this first term is giving us our cost of production and transportation across the entire global network. Okay? So that is all of our, in the typical model formulation, it's the Cij, Xij costs. Then we also have the costs of setting up low capacity facilities or high capacity facilities. So low capacity is shown here, and then high capacity is next to it. Okay? Whoops. So if we wanted to come back in here and maybe put these at 0, okay, and then come over to data and solver, the model should already be in there. If I click on options, it's not assuming non-negative or assuming linear. So let's try a couple things here. We have a very tight tolerance. Sometimes you can get the right answer when you don't restrict it. But see now, let's see what we've got here. So that does come back and give us that same answer that we had in there before I removed it, 23751. And let's come back again with solver into options. And see now, it does it precisely. So data, solver, options. Assume linear, assume non-negative. Okay. But because we're putting in binary here into this particular set of variables, and that's just in case you haven't seen this kind of constraint before, we'll talk about that. Then we still want to set it up as a linear model, but then it will do iterative branching and bounding to try to come up with a better the right integer solution. Okay, let's look at let me actually stay there. We explain everything on the spreadsheet, but not actually the solver parameters. So the target cell is the one that's highlighted in right now, and we want to minimize. So that's all clear. Changing cells, you can click on this, and this is B14 to H18. So it's all of these. Okay, already was there, but I'm just showing you it again. And then the constraints. Well, we described these in words, right, and what we needed. So excess capacities. These have to be greater than or equal to 0. We can't have negative excess capacity. Then, let's see if we... Whoops. I always forget sometimes you can't double-click on a particular field. That tries to then solve the model. So I want to change. If I want to actually look at it, I can change. And so this particular set of variables is saying all of my decision variables have to be greater than or equal to 0. So basically what's happening there, by putting that there, is eliminating the need to do assume non-negative. So technically you probably don't need to do both of those. But you wouldn't need to include that extra set if you said assume not negative here. This set's B22 to B26. Again, we can't have negative excess capacities. Now here, B28 to F28, unmet demand, not only, it's not enough just to say that we're not going to oversupply, but we're not going to undersupply a particular demand. So we want to meet it precisely. So we want to set this equal to 0. That's kind of strange how it comes in here and it actually says equals 0. I wonder if you just put 0 in there. It seems like that's the same thing. But it comes back and says equals 0. Okay, that's fine. And then binary. So this was the other one I wanted to say. So a portion of the decision variables are actually going to be binary. So when you highlight them and you come in here, you can actually choose a sense of the sign or say int or binary. Int or binary. Okay? And that's everything here. We solve it, we get the answer. Okay? All right. Let's move on to the more, I don't want to say complicated, but thorough treatment of production allocation modeling. So this other one is called network opt. You open that one. Macros have been disabled, so I am going to enable these. Now, I guess I'll need to hear if you guys have problems with that on your end, enabling macros from a file like this. If that is an issue for you, I think the only problem is that you won't be able to use these command buttons that are on each of the sheets. Not a big deal, because you can still go to Data, Solver, and the models will still be there. Okay? So let's talk about this. Let's come back to the discussion here. So I guess just to wrap up where we left off, this is the model that we just were dealing with in that first Excel file. Okay? And so you can kind of read through the chapter, follow along, where they describe what the constraints look like in both Excel terms and in an actual formulation, a mathematical representation. Okay? So it's pretty thorough for that on that side of things. Remember, I'm paying less attention to the gravity location model, so we're going to skip right over that section. And we come to network optimization, phase 4. So here we're going to base this on a problem where we have two manufacturers of fiber optic telecommunication equipment, Telecom One and HiOptic. And these two are, Telecom One is located on the eastern half of the United States, or its focus is there. Has manufacturing plants in Baltimore, Memphis, and Wichita, and it serves markets in Atlanta, Boston, and Chicago. HiOptic is on the western half of the United States, serving markets in Denver, Omaha, and Portland. And it has plants in Cheyenne and Salt Lake City. And then Table 5.2 gives us the appropriate input information, parameters, and so on. As follows. Okay? So, in this setup, as it shows here, Telecom One has a total production capacity of 71,000 units a month and a demand of 32,000. HiOptic has 51,000 units per month capacity and 24,000 units per month demand. Okay? And they independently want to evaluate how to allocate demand to their facilities. The model being used here is a demand allocation model. Okay, we don't have any facility decisions to make. Facilities are going to be open, and let's see what happens. Okay, so we're going to use this approach. If I come back to Excel, in each one of these tabs, you'll see at the bottom that formulation representation, as well as the description of the decision variables and input parameters. Okay? Okay. So I have supply cities listed over here, all 5, 6 demand cities, as well as the demands for those that are being generated by those cities. Over here, because each one of these supply cities, there's only one type of facility being considered here, and the fixed costs are shown, and the capacities are shown. Okay, all based on the data that's over here. Okay. Okay. By the way, one thing I'll ask is if you see me doing things in the presentation in Excel and you're wondering how I'm doing something, that is it's a good idea if we have you put that information out in email or in discussion boards so that we can address those things. So HiOptic and Telecom 1 are operating independently here. In particular, but we're setting this up to be generic so that when we move on to a later phase, that we won't have to change the way this spreadsheet looks. But for now, HiOptic is only going to be using those 2 facilities, Cheyenne and Salt Lake. Okay? Those are the ones that it owns. So, and because this is only demand allocation, I am going to fix these at 1. So I could put 0 in here and try to satisfy everything out of Salt Lake. But I'm going to put 1s in here and not make them decision variables. The only decision variables then become these cells in blue. Okay? This is for HiOptic. So if I go look at Data Solver, and I look at what cells can we change in this model, E15 to G16, E15 to G16. So those are the 6 cells that we can change. Okay? Now, a lot of this is similar to the model we just went through, so it helps I don't have to re-describe how things are working here. In terms of constraints, B23 and B24 both, again, the creators of these files chose to put non-negativity directly into the constraints instead of assuming non-negativity. E15 to G16. So, and it did the same thing with our decision variables. E20, wait a minute, E23 and 24. Oh, sorry, those are different ones. So it's specifically looking at B23, which is Cheyenne, and B24, which is Salt Lake. So these 2 facilities need to have non-negative excess capacity, or in other words, they can't supply more than they have. And these were the non-negative decision variables. And then here, the last set is Denver, Omaha, and Portland. We need to have 0 unmet demand. So again, this is for HiOptic, and we need to make sure that those 3 supply cities, or demand cities, are being satisfied by our 2 supply cities, Cheyenne and Salt Lake. The other data doesn't matter. It can be there, but it's not going to affect our solution. How do we know that? Well, if I come into the objective function, if I double-click on this, I'm basically turning off the other parameters. They're not weighing into my decision of cost. Only Denver, Omaha, and Portland, and Cheyenne and Salt Lake are actually being considered here. Okay? So, let's get these guesses out of here. Basically, I think it's a little test, and if you want to put together an allocation to see what happens, how close were you to actually trying to come up with a good allocation? So if I said I wanted to have them out of both, but I've got all that unmet demand, Cheyenne, let's say it supplied everything for Denver and everything for Omaha, and Portland supplied everything for Salt Lake. Is that, oh geez, I'm afraid I guessed the right answer. Let's not do that. Let's just put these numbers as zeros and let it decide. But we need to have these as ones, okay? All right. Now comes the question of whether this is going to work or not. When I hit solver, and it does, then I can go in and solve this problem. See, I must have remembered those numbers being exactly like that, so my guess was going to be correct. So anyway, this is an allocation for high optic. Same exact thing plays out for Telecom 1, so I don't need to go through that one as well. The thing you should look at here, though, let's make sure I'm not missing anything. Solver, options. Tolerance is 5%. This is something I noticed was a problem in one of the later versions. It may not be an issue here because we don't have any integer variables, so we don't have tolerance to deal with. So it's probably fine then to leave it at 5%. Linear, again, non-negative, really we don't need it because we've thrown the constraints in there already. Doesn't change anything. Okay. 21416. And this one was 42786. So I could put a total cost over here of equals this plus, and then I can click on the other sheet and just click on that value and hit enter. And now I have my total cost. All right, let's go back into the text, and it says, this is now page 125, locating plants, the capacitated plant location model. What if these two companies decided to form into a single entity? Call it Telecom Optic. So in this case, we want to open up all facilities to all regional demands, and then look at what production options we have. Okay? So we come back in here under production allocation, and in this version, what we wanted, basically what we're going to show is kind of a step improvement, a step-by-step improvement. So in this case, again, all of this is the same. We don't have to change it. All of this, these are all still decision variables. In this version, we activate all of them. Okay? And let me take that back, because I think, let me make sure, what is it doing here in terms of solver? B14 to G18. Right. I think the color coding isn't the greatest here, because back here it's showing these blue regions is what you can edit. In here, it's switching to this, but these, for this version of it, let me go to the next one, are fixed. In this production allocation, all we're going to do is say, let's say we have all 5 plants available to us. So we'll open them all up, but let's try to then take advantage of production transportation per unit costs, and we can mix and match demand to supply, as we couldn't do before. So again, all these constraints are all the same, and in terms of the cost, now you see all the distribution and transportation production costs are included, fixed costs of all facilities, and all facilities are open. Okay? So those two components are in here. That's the fixed cost and the transportation per unit cost. If I come down to the bottom of the spreadsheet, okay, it shows that it's a demand allocation only. So it seems a little counterintuitive, right? Because I've just said we have plants, we have fixed costs in here for facilities. Well, we do, but it's not a decision. We're forcing these 5 plants to be open. So technically, I don't need to put them in my objective. The only thing that's in the objective are the things that I can control. Those other costs are there. Now, they are part of the overall cost, so they'll come up here. But in terms of a decision, they're not in there. Really, I could add another term over here that's a fixed amount that has no decision variable associated with it. So when I come into Solver, that's where these variables, the changing cells, are only these, okay, not those blue ones. And then I have non-negativity, and unmet demand needs to be across all 6 demand regions. Okay? Options, linear, all that. Again, I don't have any integer or binary variables. So when I solve, I get 48,913. Okay? Just so that it didn't get stuck in the solution. You can kind of start it at 0 and you get 26, or has some other numbers. I'll just kind of get these, doesn't matter where I start. And then if I hit solve here, oh geez, yeah, you know what I did? Think for a minute, what did I do? Right, all these are 0, but they're not actually being changed in the model, so I can't do that. These need to stay open. And then what it does is now tries to find out an allocation. So let's try that one more time. And now I'm back at that solution. Interesting here is that I've opened up all these facilities, 48,913, and the total before was 64,202. So here's just a quick example of the benefits where you're merging and consolidating operations. Okay. Moving on to the location allocation problem, now we will turn on plant selection. Okay? Turning on plant selection turns on this portion of the objective function, a fixed cost of whether we open a facility, plant, or not. Okay? So, when we do that, everything else is the same. We look at here. Actually, this is no different. It still has those fixed costs in here, but now the difference is in Solver. And our changing cells include the column H. So now I'm actually going from here over to there. So now I'm allowing the selection of facilities. Now here's where I can set these all to be 0 and a couple of zeros over here. And when I resolve, it will work on all those. Since I have binary here now, this was that other constraint that I was talking about before. Now, tolerance is 5%, so this is where I'll be interested to see if we encounter a problem. The next one I actually found it. In my office, I think that the number was 47.8. Couldn't find the best solution. So I would, recommend when you have an integer model, they're tougher to solve. Ours may not be because they're small enough. But you don't want it to stop short of finding the optimal solution. And if I say 0.5%, and since I haven't pre-run this, it's still fast. And it's still the same solution. So that's the more of a recommended way to do it. Okay? 47,401. Finally, we come over to the last one. This is in the textbook. What happens when you want to single source? So there can be reasons for desiring single sourcing of a supply to a particular customer or demand region. We talked a little bit about that in the previous lecture. So when we do this, if I hit, let's see here, the one set of new constraints are requiring that demand coming from each one of these from a particular facility is supplied at its entirety. We still have, what we're doing is now forcing all of the decision variables to be binary. So really, remember, this formulation is different. And maybe I should close out and come back down here just for a minute. See here now, our x's are taking on a different meaning. And it's production, the portion of production coming, being moved between supply I, factory I, and customer J. So, so we need all of those to be 0 or 1, and then only being satisfied across for one, for a particular customer, J is 1. Across all the facilities, I only going to be supplied at a total of 1. And if I require Xij to be 0 or 1, that implies that I'm only going to get sourced from one of those facilities to satisfy all of my demand. Okay? So this one's going to require a little bit more work. And all of these variables become decision variables. There's a little button on here that says an increased sheet magnification, so I'm going to do that. Now the numbers up here are still the same. And so again, city is supplied with a 1. The resulting production allocation is just saying the demand times whether this value is 0 or 1 is going to give us the demand for that. And the reason that's important is going to be down here when we actually want to generate a cost. Those 1s aren't going to help us. We really need to know how much material is being moved from supply to demand, supply city to demand city. So we have all of these multiplied by all of the demands, and then still the fixed costs. Okay. So if I go into Solver, options, and I've got a very tight tolerance. Now, see how much this thing's doing. It ran for a while, still pretty fast. And it came up with an answer of 49,717. Now that, compared to the prior one, which was 47,401, gives us a penalty for single sourcing of $2,316, or in units, could be 2,316,000. So that's the point and illustration of everything that I've got here as far as Excel modeling. And I hope this was very helpful. We'll do a sample problem of this or as an exercise for an assignment. Okay? I think that's it. Thank you.